Today we're going to talk about properties of determinants. Let's start by reviewing some properties of determinants of order n that we discussed in the last lesson. First, we'll start off with the definition of the determinant. Let's say that A is an n by n matrix. We'll denote Aij with the tilde as that n-1 by n-1 matrix obtained from A by deleting the ith row and jth column. From here, we'll define the determinant of A recursively. If n equals 1, we'll define the determinant of A as just the entry A11. Otherwise, if n is greater than or equal to 2, we'll define the determinant as the sum over j of -1 to the 1 plus j times A1j, this is the entry in the first row jth column, times the determinant of A1j tilde. Here, we've crossed out the first row in the jth column and then taken the determinant recursively. More generally, if we have any row I, the determinant is the sum over j of -1 to the I plus j times A sub ij, this is the entry in the ith row jth column, times the determinant of Aij tilde. That is, we can express the determinant as a cofactor expansion along any row I, even though the definition of the determinant corresponds to I equals 1. Next, the determinant of A is 0 whenever either A has a row of zeros or when A has two identical rows. We're going to use this today to talk about more properties of determinants and how they're related to elementary row operations. First, let's remind ourselves what an elementary row operation is. Let's say that A is an m by n matrix. Here, m is the number of rows and n is the number of columns. Recall that there are three types of operations that we can perform on the rows. There's type 1, where we interchange any two rows, type 2, where we multiply a row by a non-zero scalar, and type 3, where we add a scalar multiple of one row to another. We can also perform these operations on the columns as well. These three are called the elementary row operations. Similarly, they're called the elementary column operations. An elementary matrix is an n by n square matrix E, which is obtained by performing exactly one of these three operations on the n by n identity matrix I sub n. Let's say that more generally A is an n by n matrix. And let's say that B is obtained from A by performing one of these elementary operations. First, let's say that B is a matrix obtained by interchanging any two distinct rows. Then the determinant of B is negative the determinant of A. Next, let's say perhaps that B is obtained from A by multiplying one row of A by non-zero scalar k. Then the determinant of B is k times the determinant of A. And finally, let's say that B is obtained from A by adding a multiple of one row to another. Then the determinant of B is the same as the determinant of A. We'd like to explain how to prove this. Let's denote lowercase a1, lowercase a sub 2, and lowercase a sub n as the rows of A, and let's say that B is obtained from the matrix A by either interchanging rows A sub r and A sub s, where r is less than s, multiplying row A sub r times the scalar k, or adding c times the row A sub s to the row A sub r. To make our proofs a little bit simpler, let's denote x as k times A sub r plus c times A sub s as a linear combination of the row A sub r and the row A sub s. We're going to denote c as that n by n matrix obtained from A by replacing row r with this linear combination x. We're going to expand the determinant of c along row r. Again, remember that c is obtained from A by replacing row r with this linear combination x. According to the theorem we just explained, we can actually expand along row r to find the determinant as above. Notice here that x sub j is the element in row R, column J, because we've replaced row R with our linear combination x. Also, we have here a sub rj tilde, because remember that if we cross out row R of C, then we just get back the matrix A. Specifically, we get back A tilde. Now, let's replace the linear combination x with k times a sub r plus c times a sub s. We can now expand using distributivity, and we're going to stare at these two expressions here for one moment. Let's take a look at the first expression, this capital A sub rj times the determinant of arj tilde. If we stare at that, then we see that this is simply the definition of the determinant of A, where we've expanded along row R. Now let's take a look at the second expression, the sum, where here we have A sub sj times the determinant of arj tilde. Well, if we ignore the A sub sj, that entry, then it really looks like the sum here corresponds to the determinant of A. But the A sub sj is the one term that seems to be throwing things off. It's almost as if we had row R and actually replaced that with row S. But this is indeed the case. This second sum would have to be 0 because it does look like the determinant of a matrix where rows R and rows S are both equal to just row S. Since the two rows are equal, we see that the determinant does have to be 0. So we see that the determinant of C is k times the determinant of A. Now, we claim that we can actually prove the first two statements of the theorem just from this expression here. Let's say, what if we set C equal to 0? Then according to the way we've defined x is k times A sub r. So this means that we've actually obtained a matrix B by multiplying row R by a scalar k. So this means that the determinant that we find is k times the determinant of A. On the other hand, let's say that we set k is equal to 1. So now our row R looks like x, which is AR plus C times A sub S. This means that we've actually added a multiple of row S to row R. But because k is equal to 1 and C can be anything, we see that we just return the determinant of A. So this does indeed prove the first two parts of the theorem. Now let's prove the hard part. Let's say that B is obtained from A by interchanging rows R and S. Recall that our matrix C is that n by n matrix obtained from A by replacing row R with this linear combination X. Now let's let C prime be that matrix obtained from C by replacing row S with X. This means what we've done is we've taken the matrix A and we've replaced both row R and row S with the linear combination X. Now let's expand the determinant of C prime along row S. Well, as just mentioned, the two rows of C prime are equal, namely row R equals row S, which is this linear combination X. But we're going to expand along row S. We see that row S contains the linear combination X. Otherwise, we can just cross out row S. This is the C sub Sj tilde. The reason why this is C instead of C prime is remember that C prime is obtained from C by replacing row S with X. So if we cross out row S, then we just find CSJ tilde. Now we'll do the same trick as before. Remember that X is a linear combination, k times A sub r plus C times A sub s. So we can use the distributive laws and expand things out in the way you see here. Just like before, let's stare at these two expressions. The very first expression, the sum A sub rj times the determinant of C sub sj, is the determinant of some matrix where it appears that we have an expansion along row S. This is the S negative 1 to the S plus j times the determinant of CSJ tilde. But it seems that maybe in row S, we've replaced the row A sub r. In the second sum, we do have a sum A sub Sj times the determinant of C prime, C sub Sj, and if we stare at this now is an expansion along row S, but in row S, we have A sub S. Remember that this here is really just the definition of C. So we see now that the expression we get is K times the determinant of some matrix C double prime plus lowercase c times the determinant of capital C. As mentioned before, C double prime is that n by n matrix obtained from C by replacing row S with A sub r. Here, C double prime can be obtained from A by replacing row R with the linear combination X and replacing row S with row A sub r. Finally, we're going to expand the determinant of C double prime along row R. Remember that C double prime is obtained from A by replacing row R with X and row S with A sub r. So we have an expansion, just as we had before, where X we can write as K times A sub r plus C times A sub S. We then have distributivity, and just like before, we'll stare at these expressions here. For the first sum, we have a sum over A sub rj times the determinant C double prime rj tilde. Here, this is an expansion along row R, but now notice that we've replaced row R of C double prime with A sub r. But here, C double prime had row S equal to A sub r. So this sum here is the determinant of a matrix that looks like A, but both row R and row S are equal to A sub r. So this first expression you expect to be 0. For the second expression, we have a sum A sub Sj times the determinant C double prime tilde sub rj. This is an expansion along row R, but we've replaced row R with A sub S. But remember how C double prime is defined. Row S is A sub r. So this expression here actually corresponds to the matrix B. Remember that matrix is obtained from A by interchanging rows R and S. So this sum is equal to K times 0. Again, the 0 comes from seeing that the expression is really the determinant of a matrix that has row R equal to row S, which is equal to A sub r, plus C times the determinant of B, and again remember that B is that matrix obtained from A by interchanging rows R and S. So putting all of this together, now using the expression that we had before in terms of the determinant of C prime, we now see that 0 has to equal to K times C times the determinant of B plus the determinant of A. But this is true for all scalars K and C. So this means that the determinant of B is the negative of the determinant of A, as was the third part of the theorem. As a special case, let's consider the elementary matrices. Remember, these are the matrices that we found by performing an elementary row operation on the n by n identity matrix. If E is obtained by interchanging two distinct rows, then the determinant of E is negative 1. If E is obtained by multiplying one row by a non-zero scalar k, then the determinant of E is just equal to k. And finally, if E is obtained from the identity matrix by adding a multiple of one row to another, then the determinant of E is just 1. Again, this here more or less follows from the previous results, but we have to actually show one thing. That is that the determinant of the identity matrix is equal to 1. We're actually going to prove a much more general result. We'll prove that if we have an upper triangular matrix, this means that everything below the diagonal is 0, but we don't yet know anything about what happens above the diagonal. We'll prove that the determinant of such a matrix is the product of the diagonal entries. Here the diagonal entries are the elements d11, d22, all the way down to d sub nn. We're going to prove this by induction. So let's consider the following statement as a function of an integer n. Let's let D be an n by n upper triangular matrix. Then the determinant of D is the product of the entries along the diagonal. Let's establish the base case first. Proposition P of 1 is true because if D is a 1 by 1 diagonal matrix, then its determinant is just that one entry, D11. This is by the definition of the determinant. Now let's assume the inductive hypothesis. That is that the proposition P of n sub 0 is true for some integer n sub 0. We'll perform now the inductive step. So let's consider proposition P of n0 plus 1. If we let D be an n0 plus 1 by n0 plus 1 upper triangular matrix, then remember that D sub ij is 0 whenever I is greater than j. Now, since we have lots and lots of numbers that are 0 below the diagonal, let's use the theorems that we proved in the last lecture to write out the determinant of D by expanding on the last row, the very bottom. This means that almost all of the entries that we have in our sum are 0. That is, the D of n0 plus 1 comma j will be equal to 0 unless j is equal to n0 plus 1. So the determinant now is equal to the last entry in the lower right-hand corner, D sub n0 plus 1, n0 plus 1, times the factor matrix D n0 plus 1, n0 plus 1, tilde. But because we've crossed out now the last row, last column, this D tilde is actually an n0 by n0 upper triangular matrix. So, invoking the inductive hypothesis, we see that the determinant of D tilde is again just the product of the elements along the diagonal. And putting all of this together, we actually do see that the proposition is true by induction. Thanks very much for watching.